Okay, we're ready to start talking about a new topic, and that is synchronization. Now that we know how to create threads, we can get into all kinds of trouble with them. And it's important for you to be prepared for that trouble. So we need to talk about synchronization. So the idea of synchronization is that what we're trying to do is we're trying to manage the dance between multiple threads so that one thread doesn't womp on another thread. That's basically the idea. Now, when one thread does something that interferes with another thread, we call that a race condition. And there are lots of ways that you can trigger race conditions. So you have to watch out for them. I'm going to talk about some properties that of programs that are going to have race conditions. And just to help you understand where we're headed, so the discussion about p-threads and now the discussion about synchronization is getting you ready for a set of problems that I'm going to ask you to do that are problems that require threads to solve, but are also going to trigger potential race conditions. And then you're going to need to manage those race conditions using synchronization techniques. And while you're working on that, we're also going to be exploring some classical inter-process communication problems that trigger these race condition behaviors, and we're going to talk about solutions to those problems. So you're going to get to experience in class some problems that require synchronization to solve race conditions. And then you're also on your own going to have a novel set of problems to work on that require you to use synchronization to manage the race conditions that you'll trigger. And these problems are not trivial. They're really good. It's going to be a good experience for you because I feel quite strongly that by the time you get through those problem sets, you will be a competent multi-threaded programmer. And you'll be ready when you leave Stonehill and you end up at a job that's asked you to write multi-threaded code. You'll be ready for the kinds of problems that you're going to encounter when you write multi-threaded code. All right? Okay, so let's talk about race conditions. All right, what I want to do is just draw a picture of a potential problem that's going to trigger race conditions. So here's a print spooler or print queue. And on the print queue, we're going to have some files that need to be printed. So here's a file, abc.txt. And here's another file, program1.cpp. Here's another file, paper.pdf. So these are all files that need to be printed. All right, so the queue has sort of a front and a back to it. So let's assume that, I think I want to put the arrow here. Let's assume that we have a variable called front. And front currently has the value of 4. And let's also assume that we have a variable called let's assume that we have a variable called back. And back points to the slot that has the next location where a file can be placed in the print queue. So 4, 5, 6, 7. So back is going to have the value of 7. Now, this is a resource, all right? And it's a resource that's shared between multiple processes, all right? And so one of the processes is process A, which is continually adding things to the print queue. Another process is process B, which is also continually adding things to the print queue. So what could possibly go wrong? Well, let's go through a scenario of what happens, all right? So here's what process A and process B are going to do, all right? Process A is going to check the queue for empty slot, and then it's going to place file at empty slot, and then it's going to increment empty slot position, okay? And then wait for another file. Actually, I think we'll put that up at the top. Wait for next file to print. Okay, so these are the steps that are being followed by our friend. Move that up here. Our friend process A. But the thing is, process B also follows these same steps. So, oops, what I'm going to do is I'm going to copy this, or I'm going to move this, and we'll copy it. All right. Yeah, I'm not really happy with that. Let's move this down here, and I'm going to use the awesome power of this tool to just shrink it a little bit. Okay. And then we're going to copy that and paste it right here. All right, cool. Now, what I want to do next is I want to imagine this is process A. We'll call this process A right here, and this is process B, okay? All right, now, let's think about a scenario that will trigger a race condition here, okay? So imagine that process A now has a file that it wants to print. So it wakes up and says, oh, I've got, I'll change the color of my pen here. I've got pa.pdf. pa.pdf that I'd like to print. And at the same time, since we're using concurrency and process A and process B can both run at the same time, process B says, oh, I have a file I want to print, pb.pdf. See, I just lost that for a second. Okay. So process A says, I have pa.pdf I want to print, and process B says, I have pb.pdf that I want to print. So they both want to print at the same time. All right, so watch what happens here. We're going to, on process A, we're going to check the queue for an empty slot. And process A goes, yep, there's an empty slot, and the slot number is slot number 7. Okay? So back has the value of 7. Process B goes and does the same thing at the same time and says to the print queue, hey, do you have an empty slot? Print queue says, yep, I sure do. It's slot number 7. So back has the value of the number 7. That's the slot. Now you see where this is going to go. It's not going to end well. So process A is told to place the file in the empty slot. So what it will do is it'll place pa.pdf into the empty slot. But so we'll just check off that these are the things that have happened. And process B also wants to place a file in the empty slot. So it's going to overwrite PA and put pb.pdf into this empty slot. So we have now just wiped out PA. Then process B seems to get a little bit more attention from the gets a little bit more attention from the from the processor. So it increments the empty slot position and says the empty slot position is now back is number, it has the value 8. And process A says, okay, well, I need to increment the empty slot position. So it's going to set back also equal to the number 8. So back will be changed to 8 by process B, and then it'll get changed to 8 again by process A. Yikes. So this is an example of a race condition. It's a race condition because we have two processes and we have a shared resource, the print queue, and the processes are competing for the attention and use of the shared resource, and they're effectively interfering with each other. So what we would have liked to have happen is if there was some way to slow things down, so let's say when process A looks at the queue, we effectively block process B from messing around with the queue while process A is messing around with the queue. That would allow process A to get in, load up the queue with its PA, and then let process B run and load up the queue with its PB. So let's actually take a look at how that might work. All right. So, well, I guess I'll just say that an easier way of thinking about this is if we just let process A and process B run whenever they want, they can interfere with each other. But instead, if what we do is we say, what if there's some magical thing that we could do that identified the section of code in process A that needs to mess around with the queue, and the section of code in process B that messes around with the queue. And we did this. We said, the moment that process A returns with a file to print, it locks process B out of messing around with the queue until it's done messing around with the queue. All right. So that would let process A put its file into the queue and increment back, and there's no problem. We're not overwriting back, and we're not overwriting files. The same thing with process B. What if process B is allowed, once it returns with a file that it wants to print, and it wants to go get the attention of the queue, it basically blocks process A from working with the queue until process B is done working with the queue. So if these two processes are able to block each other from messing around with the queue at the same time, then we can eliminate the race condition. So when you do that, when you have one process block another process from doing something for a short period of time, that is called synchronization. So the process of placing synchronization, essentially, where I think I over-spec'd it here. So let me draw that again. So it would just be these three statements: the check queue for empty slot, place file at empty slot, and increment empty slot. Those three statements are the ones that need to block the other process from executing. All right? We're in an unsafe area if we start messing around with the queue. So block the other process from messing around with the queue, and things will work out okay. All right, so how do you know when you have a potential race condition? So the way you know is you look for these symptoms. All right. Number one, do you have read-write access to a shared resource? Okay. If the answer is yes, and in this example, we certainly did, right? We had read-write access to the print queue. All right, so that would be one sign that you've got a race condition. Number two, are there two or more threads or processes that have read-write access to that shared resource? In this example, we did have that problem, right? We had a process A and a process B, right? If you have that situation, read-write access, and two or more threads or processes, you are going to have race conditions, guaranteed. So you don't even have to try to find the race condition. If you answer these two questions yes, you are going to have a race condition. So all the problems that I'm going to ask you to do that involve synchronization are going to have read-write access to a shared resource and two or more threads and processes. In some cases, you can have many, many more threads and processes running. Okay, so when you have the race condition, you have sadness. Why? Because the resulting execution of the threads and processes is non-deterministic. All right, and this is a huge pain to debug, as you are going to discover as you work on these problem sets that I'm going to give you. Because they're non-deterministic, it means every time you run these programs, the output could be different. So if I go back to here and I say, okay, let's consider this print queue example. Sometimes, if we don't have synchronization, you would take away those little orange bars that are here and here, we don't have synchronization, then sometimes process A will put its PDF on the queue and process B will put its PDF on the queue, no problem. Sometimes process A will get to put its PDF on first, and sometimes process B will get to put its PDF on first. So when you run these programs, if you're trying to debug, well, I'm having problems with the print queue, why is it not working? Sometimes you'll see process A.pdf, PA.pdf get printed first, and then PB.pdf get printed second. Sometimes you'll see PB get printed first, and PA.pdf get printed second. Sometimes you'll see only PA.pdf get printed. And sometimes you'll see only PB.pdf get printed. Sometimes PA.pdf will print incorrectly because part of PA has been written over by PB, but not all of it. And the same thing's true in reverse. Part of PB could get printed out with part of PA kind of overwritten inside PB. So you're going to end up with a huge mess. So every time you run the program, different things are going to happen, and that is going to drive you crazy. So the best thing to do is to look at your code and say, do I have read-write access to a shared resource? We sure do with the print queue. Do I have two or more threads and processes running? We sure do with that print queue example. Then we have a race condition. How do we solve, or how do we fix race conditions? We use synchronization. So synchronization will slow the execution of the processes down so that they don't interfere with each other. All right. Now, how do we slow the processes down? How do we coordinate the execution of these processes so that one process doesn't womp on another process once we've identified a race condition? Well, this is what we do. The first thing we're going to do is identify something called a critical region. So a critical region is a section of code that we're going to apply synchronization to. So it's the code that is doing this, that has read-write access to a shared resource, and that I guess that's the simplest way to think about it. It has read-write access to the shared resource, and you know that two or more threads or processes with that read-write access are womping on that read-write access. So that's the critical region. All right, so what we're going to do then is we're going to apply synchronization to the critical region of your program. Okay, and when you do that, it ensures only one process or thread has read-write access to the shared resource. One thing that you must be aware of, okay, and I'm putting exclamation points here, the critical region is not the entire program. I'm saying this for two reasons. Number one, I've experienced this in the field. I've gone out and worked with developers improving the performance of their code, and they'll sit down with me and we'll kind of review the code, and I'll say, all right, yeah, it looks like, so you're using concurrency. Yep. Okay, well, what about race conditions? Oh, we got race conditions covered. We've got synchronization in our code. And I look at their code, and the synchronization starts on the first line of the main program and ends on the last line of the main program. This is not good because it effectively makes the entire program the critical region, and it means that while that program is running, other threads and processes cannot run. And so what effectively, if your critical region is too large, you've basically defeated the concurrency that you're trying to achieve to get improved performance in your program. So you're looking for the critical region should be the minimal amount of code that triggers the race condition. Okay, that's where the critical region should be. All right. Now, if we go back up to our example here, you can see that I've got a critical region identified as the code that checks the queue for the empty slot, the code that places the file in the empty slot, and the code that increments the empty slot. All right. I don't have the code that's waiting for the next file to print. You can imagine that that might be like a dialog that pops up to the user that says, hey, can you identify the file for the next file to print? Okay, that dialog and user interaction can take a very long time. If we made that part of the critical region, then we would be blocking every other program out there, every other process from using the print queue while we're waiting for the user in process A to select the file to print. That is incredibly wasteful. We want to make sure that we only apply synchronization to the section of code that actually triggers the race condition. So waiting for the next file to print does not trigger the race condition. So I'm hoping that makes sense. We're looking for that minimal set of code that's going to trigger the race condition. That's the critical region. Now, is it easy to find that? No, it's not easy. It takes some work and effort and practice, and you're going to get that with the homework assignments. And we'll do examples in class as well. All right, so here is the thing. Once you apply synchronization to, okay, so a couple of other things about critical regions. I'm looking at my notes and I'm thinking that doesn't, okay. So just something to watch out for. I'm changing color here. Let's go back to purple. I'm kind of liking purple right now. Okay. So here's another exclamation point. This is another common error that students make. Watch out for assumptions about timing in these sections. So like if you, in order for your program to work, if you have to add things like sleep that puts your program to sleep for a little while, or a for loop that runs up to a very large number that kind of slows your program down. In other words, you're changing the timing of the execution of your program, and you notice, hey, my program works if I put a sleep in here. That means that you're not doing a good job of using synchronization on your critical region, or you haven't correctly identified your critical region in its entirety yet. So be careful about that. All right, so you're probably wondering, I keep using the term synchronization, I'm saying it over and over again, but what does synchronization look like? Well, there's a bunch of different ways of doing synchronization, but a very common technique of synchronization is called mutual exclusion. And there are a number of techniques for doing mutual exclusion that we're going to examine, okay? And so here they are. There's two main flavors. There's something called busy waiting to get mutual exclusion. And the techniques of busy waiting are disabling interrupts, using lock variables, strict alternation, something called Peterson solution, and the test and set lock instruction. So we're going to look at lock variables, Peterson solution, and the test and set lock instruction. All right, and then also there's a few other techniques that don't involve busy waiting. So the thing about busy waiting is we're eating CPU to force synchronization. And a simple way to think about that is we're spinning around in some kind of loop. waiting for something to happen. And when that happens, we continue execution. But because we're spinning around a loop, we're eating up CPU. That process of waiting and spinning around the CPU is incredibly expensive and basically resource intensive, and it's not really a good idea. So the operating system provides some mechanisms that are superior to busy waiting. So a couple of those are sleep and wake up. I guess I would call these, I'm going to categorize them as non-busy waiting. And so we have sleep, we have semaphores, and monitors. So we're going to look closely at semaphores and monitors. Every once in a while, we'll experiment a little bit with sleep just to change the behavior, but sleep by itself doesn't do the best job of mutual exclusion. So the idea of mutual exclusion is that we're going to, when we use it, we're going to block other processes or threads from running while we've turned that mutual exclusion on in our process or thread. So for example, process A, when it's using mutual exclusion, okay, mutual exclusion would start here and it would end here. So while the mutual exclusion's in effect, process B is not allowed to run this code here. It's not allowed to run this code. All right, and the same thing's true for process B. When process B triggers the mutual exclusion, however it does it, that blocks process A from running. So that's the idea of mutual exclusion. And these are all just different ways that you can implement it. Okay. That is a pretty good start.